Hey guys, it's Mr. Odell. So this is going to be our first YouTube video that we're doing, just to try to make things a little bit easier on you guys. So we're doing what's called asynchronous learning. So you guys are going to get a YouTube video either the day before or maybe 2 days before our Teams meeting. So the YouTube video is going to be the lecture because, well, me sitting there and using a Teams meeting for lecture is kind of boring. And we're going to treat our Teams meetings as times to review assessments. Treat it like office hours where you guys can ask questions and maybe just work through some problems together just to make sure everybody's on the same page. So with that being said, we're going to get going. I'm going to try to keep videos to under 10 minutes just to make it a little bit easy. Make it easy on those of you that have bad internet. That way your computer or phone or whatever you're watching this on has the ability to sit there and buffer the video in a reasonable time frame. And that way you can watch it once it finishes buffering. So with that being said, we're going to jump into our PowerPoint. If you guys remember what we left off on right before Christmas, we were talking about quantum numbers in chemistry 2. In chemistry 1, we were talking about the wave mechanical model. So our next major topic that we're going to move into is electron configurations. So let me pull up the video real quick. Or sorry, not pull up the video, but pull up the PowerPoint real quick. And I'm going to shrink this camera. That way you guys can see the slide. So first quick question. So we have this idea of an orbital. So what are my types of orbitals and how many electrons can each hold? So take a second, pause the video, think about your answer, say your answer, and come back. So at this point, you should have come up with an answer. So our types of orbitals. So if we think about it, I'm going to have s orbitals. An s orbital can hold 2 electrons. P orbitals can hold 6 electrons. D orbitals can hold 10 electrons total in that sublevel. And f orbitals can hold 14 electrons in the f orbital sublevel. Notice each individual orbital only still holds 2 electrons, even though my 3 p orbitals in my sublevel hold 6 total. So whenever we talked a little bit about our periodic table and how we see recurring trends in each row. So we see the same thing with our orbital groups. So my S block is always going to consist of groups 1 and 2. So my alkali and alkali earth metals on my periodic table. So those 2 tall columns on the left. My P block is going to consist of groups 13 through 18. I'm using the nomenclature for the groups based off of the periodic table from the back of your textbook. Our D block is going to consist of groups 3 through 10, which are transition metals, and our F block is going to consist of the lanthanides and actinides. So what this means is the last electrons in an alkali or alkali earth metal is going to be in s orbital. For groups 13 through 18, my last electron is going to be in my p block. For my transition metals, it's going to be in my d orbital, and for my lanthanides and actinides, it's going to be in an f orbital. So you guys might remember us talking about the wave mechanical model just before the break. So the wave mechanical model proposes that each electron circling an atom's nucleus occupies a specific orbital and spins a certain direction. And that the orbital is like a cloud or a wave of energy, so it's not actually a ring like what you would expect, like for Earth's orbit around the sun or the moon orbiting Earth. So it's more of the probability of finding an electron in a certain space. So whenever we're talking about applying our wave mechanical model to our electron configurations, there's a couple different rules that we need to know. So our first major rule, we have what's called the Aufbau principle. So the Aufbau principle says no 2 electrons have the same set of quantum numbers. So in other words, they can't occupy the same energy levels and the same space. So 2 electrons that are in the same energy levels are going to have a different space. So our next rule, our Pauli exclusion principle. So no 2 electrons have the same spin. So if I have orbitals in roughly the same space, they're going to have opposite spins to counterbalance each other. And our last rule, we have Hund's rule. So Hund's rule states every orbital in a sublevel is singly occupied before any orbital is occupied. And all electrons in singly occupied orbitals have the same spin. So what this means is if I'm looking at my sublevel of p orbitals, I have to fill each p orbital in that sublevel with one electron, and each electron in each of those orbitals has to have the same spin. Either they all have to be upspin or they all have to be downspin before I can fill in a second a second electron in one of those orbitals. So with that being said, for those 3 rules, make sure you know them. They're really important. So for electron configurations, there's 2 forms we're going to talk about. Our first form is called a box or a line diagram. I'm going to illustrate a line diagram on the PowerPoint because it's a little bit easier to do than a box diagram. I can freeform a box diagram on Tuesday to help you guys visualize it. And our second is going to be called an orbital diagram. So for a box or line diagram, we see them as, for line diagrams, which I have illustrated below, we notice that we have a line, and that line has arrows on it representing the spin of our electrons. Excuse me. So each arrow in a box or line diagram represents an electron, and each arrow is showing the spin of that electron. So if I had 3, if I didn't have any of these double filled, all my arrows would have an upspin, or all my arrows would have a downspin. And then obviously if I were doing a box instead of a line, it would just be a box with the arrows inside the box. For my orbital diagrams are going to use a couple of different nomenclatures. Our first nomenclature is going to be an energy level as a number. My second one is going to be an orbital value, which is going to be S, P, D, or F. And my third is going to be a superscript number. That superscript number tells me how many electrons are in that orbital sublevel. So we're going to look at examples, and we will jump into it on hopefully Tuesday. I'll post another video with this practice. Probably won't be until tomorrow morning though. Okay. Alright guys, so that's going to be it. We're going to have a video working through that practice. It's going to be a mix of I do, we do, you do. So I'm going to work some. We're going to work some as a group on Tuesday, and then you're going to be free to go work whatever other ones we didn't work as a class or me individually work. So I will see you guys Tuesday.